Okay, so let's continue our discussion on inner product spaces. So in the previous lecture, as far as I remember, we ended the lecture on after discussing about the concept of geometric dimension and algebraic dimension. So let me just quickly recall what I said. So precisely, we talk about two dimensions, two dimensions. One is called the geometric dimension. One is called the geometric dimension, and one is called the algebraic dimension. Right. So, what we actually try to say is in the previous lecture is that a geometric dimension is the number of possible mutually orthogonal vectors, right? Number to maximum number of mutually orthogonal vectors in a vector space, right? Okay, or precisely you can say it as the total number of maximum possible mutually orthogonal directions vector space like that as well. And algebraic dimension was basically the number of elements in an arbitrary basis of the vector, right? So, and we had concluded the fact that geometric dimension is always less than or equal to the algebraic dimensions, right? That uh, you know geometric dimension is less than equals to the algebraic dimension, and the question we wanted to solve was that whether an equality exists or not, right? So whether an equality exists. Now, when can an equality exist? Now, first of all, let us just go through a very simple observation. That is, for example, so one sec. Should I remove this? Yeah, correct. I guess I should remove this. Okay. Now, when should equality exist? Now, algebraic dimension. This precisely gives the number of elements in the basis in a basis of an inner product space, and the geometric dimension gives the number of mutually orthogonal directions in B. So for equality to exist, the only thing which we need to focus on is if in any way we show that there exists as much mutually orthogonal vectors or mutually orthogonal directions in an inner product space V as there are elements in a basis. Or in other words, there exists an orthogonal basis in any finite dimensional inner product space, right? So my claim is for a finite dimensional inner product space, there exists an orthogonal basis, right? Now this claim is supported by examples under Euclidean spaces, right? Because if you consider R3, then we know that the algebraic dimension of R3 is precisely 3, right? You can span R3 by the vectors, unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Two observations which precisely come out from here is that firstly, this basis is an orthogonal basis. Secondly, if I simply go by the geometric structure of R3, then there are exactly three mutually orthogonal directions. And the same you can extend to R4, R5, or arbitrarily any Rn. Now, pictorially you cannot, draw out these spaces, but I guess intuitively you can extend this because you just need another axis which is perpendicular to both, to all the three which are present here, and then you will get four mutually orthogonal directions in R4. Similarly in R5, and can go on and on till Rn, right? So and our claim is actually true, and that is what we call the Gram Schmidt orthogonalization process. Okay, so let me just state this and prove it. So the Gram Schmidt I guess this is the perfect spelling. GRAM SCHMIDT orthogonalization process. Okay. Now, this is not the statement of the theorem which I claimed, but the theorem, the proof of the theorem which I'm going to state is constructive, and this construction is what we call the GRAM-SCHMIDT orthogonalization process. The theorem is and it's as simple as we just stated, that you have an orthogonal, you have an orthogonal basis in any inner product space. So it can be framed like this. Let V be an inner product space, and let beta 1, beta 2 till one sec, and let beta 1, beta 2 till beta n be linearly independent vectors, let's say, linearly independent vectors in V. Clear? So what I claim is that then we can construct orthogonal vectors. We can construct orthogonal vectors alpha 1 till alpha n, such that for all k is equals to 1 to n, the set alpha 1 till alpha n, alpha k is a basis for the subspace spanned by the vectors beta 1 till beta k. Okay, so this is actually not this statement is actually not restricted to um, to finite dimensional spaces, and that's why I wrote this statement in a different manner. But obviously you can observe this out from here, that if I consider an inner product space which is finite dimensional, then you can just consider these these linearly independent vectors to constitute the basis, right? And then whatever I claimed would be a direct result of this proof. Okay, so let's give a proof of this, and the proof, as I said, is what we call the GRAM-SCHMIDT orthogonalization. So proof. What we do is that we, sort of, this GRAM-SCHMIDT orthogonalization is sort of an inductive procedure to construct each of these orthogonal elements. So to have an inductive procedure, what we first do is we fix the first element. So we let alpha 1 to be beta 1. And then based on this, we construct the other elements. How do we do that? We claim it in this way. Suppose you already have m such vectors. Okay. Suppose alpha 1 till alpha m, where 1 less than equals to m less than n have been chosen, such that for all k, where k is less than equals to m less than equals to 1, the set alpha 1 till alpha k is a basis for the subspace spanned by beta 1 till beta k. Okay, so what we actually do is that we assume that we already have m vectors which abide by the hypothesis we have in the theorem, and using these m vectors we construct the m plus 1th vector. Okay, define alpha m plus 1, that is the m plus 1th vector which we require to be beta m plus 1. Beta m plus 1 we already have because we already have n elements, right? N elements beta m. So beta m plus 1 minus summation k equals to 1 to n inner product of beta with alpha k upon the norm of alpha k squared times alpha k. Clear? I guess here we have beta m plus 1. I'm sorry, there is nothing called beta. Here we have beta m plus 1. Correct. Yeah. Okay. Okay. So now, first thing which we need to observe is that whether alpha m plus 1 fits in our set or not. Okay. Firstly, alpha m plus 1 is non-zero, as if 0. If not, then I can just bring this to the left hand side. Then beta m plus 1 is a linear combination of alpha k's, but by our assumption alpha k is actually they span the subspace which is spanned by these beta k's, right? So if beta m plus 1 is a linear combination of alpha k's, then beta m plus 1 is a linear combination of beta k's as well, right? Where k ranges from 1 to m, right? But which contradicts the linear independence of the beta k's, right? Okay. So therefore beta m plus 1 needs to be non-zero. This is the first thing. And secondly, therefore we can think about them being orthogonal, right? Because we have already seen that since alpha m plus 1 is non-zero, therefore there is a chance of this collection to be linearly independent. Because if it would have been 0, there would have been no chance of constructing an orthogonal set, right? So now checking whether it's orthogonal, it's quite easy, because if I choose any index j for 1 less than equals to j less than equals to m, then the inner product of alpha m plus 1 with alpha j, then this comes out at inner product of beta m plus 1 with alpha j minus, we have summation k equals to 1 to n inner product of beta m plus 1 with alpha j divided by the norm of alpha k squared, and here we have the inner product of alpha k with alpha j. But we already know that this collection alpha j, where j ranges from 1 to n, it's orthogonal. That's by our induction hypothesis. So if it's orthogonal, then we know that the inner product of alpha k to alpha j is 0 for all k not equal to j, and it's 1. It's equal to it's non-zero, or it can be written as the norm of alpha k squared as j equals to k, right? So if I take this summation through k equals to 1 to n, then every element will cut out to 0 except the element where k equals to j, right? So therefore, if k equals to j, then this part becomes norm of alpha j squared. Here we have in the denominator at that point we have norm of alpha j squared, because k equals to j at that point. So these two cancels out because they are obviously non-zero, and hence we are just left with inner product of beta m plus 1 with alpha j. So this is equals to inner product of beta m plus 1 alpha j minus inner product of beta m plus 1 alpha j, and hence it's 0. Therefore alpha m plus 1 inner product of alpha m plus 1 with alpha j is 0 for all indices j1 to m, and that implies that the collection alpha 1 till alpha m plus 1 is an orthogonal basis. Is an orthogonal basis for the subspace spanned by beta 1 to beta m plus 1. Now, how can we say it's a basis? So it's a very typical observation, because since we have constructed an orthogonal set, we know that it's already linearly independent, right? So if it's linearly independent, then we have a linearly independent set where there are m plus 1 elements. So we can use it as a basis for a subspace which is spanned by m plus 1 linearly independent elements. So we choose that subspace to be the one spanned by beta 1 to beta m plus 1, right? That's the simplest case we have, right? Okay. Um, I should probably give an expanded structure of how this vectors can be structuralized by the Gram Schmidt orthogonalization process. For example, if I consider R4 and I have the linearly independent vectors beta 1 till beta 4, and I just want to give the expansion of uh, the orthogonal vectors which we have constructed through the Gram Schmidt orthogonalization process. So we have alpha 1 to be equals to beta 1, then alpha 2 will be, so alpha m plus 1 was beta m plus 1. So in this case you have alpha 2, that's alpha 1 plus 1. So you have beta 1 plus 1 beta 2 minus, then we had a summation k equals to 1 to m. M in this case is clearly 1 because we are speaking about beta of m plus 1. Beta 2 you have here, so m is equals to 1. So we just have a single element in the addition part. The inner product was with beta m plus 1, so beta 2 with alpha 1 upon norm of alpha 1 squared times alpha 1, right? Okay. Similarly, if I construct alpha 3, then alpha 3 would be beta 3 minus, so we have a summation k equals to 1 to 2 in this case, 1 to m, because this 3 is basically 2 plus 1. So we have summation k equals to 1 to 2, so we will have precisely 2 elements. And how will these elements come? So you have inner product of beta m plus 1, so beta 3 with k equals to 1 to n. Yes, summation k equals to 1 to n, inner product of beta m plus 1 with alpha k upon norm of alpha k squared with multiplied with alpha k. So k starts with 1, so we have alpha 1 upon norm of alpha 1 squared times alpha 1 minus, because you had the summation, so and outside you have minus sign. So here you have beta 3 with now k equals to 2, so you have alpha 2 upon norm of alpha 2 squared times alpha 2, right? Right. And similarly you can construct alpha 4. So alpha 4 is beta 4 minus inner product of beta 4 with alpha 1 upon norm of alpha 1 squared times alpha 1 minus inner product of beta 4 with alpha 2 upon norm of alpha 2 squared with alpha 2 minus inner product of beta 4 with alpha 3 divided by norm of alpha 3 squared times alpha 3. Yeah, got it? Okay. So this is the way we can expand out the Gram Schmidt orthogonalization process in order to construct each orthogonal elements of each orthogonal basis, provided a basis is already given to us. Okay. What's the important corollary of this? One which I have already stated, that if you consider a finite dimensional linear product space, then you can always construct an orthogonal basis to it, provided you already have some basis of it using this Gram Schmidt orthogonalization process. But there is something more which we can say, and that is that every finite dimensional inner product space has an orthonormal basis, has an orthonormal basis. And I guess this is pretty obvious to observe, because suppose now we already know that it has an orthogonal basis. Suppose alpha 2 till alpha n is an orthogonal basis of V, where V is the finite dimensional inner product space we are speaking about. Okay. Then the collection. So what do we do is basically we choose each element from the orthogonal basis and divide it by its norm. So then the collection alpha I by, suppose this I write as big alpha. So alpha I by norm of alpha I such that alpha I belongs to big alpha. I ranges from 1 to n is the required orthonormal basis. Is the required orthonormal basis. Because the denominators will precisely come out as scalars, so we will be left with the inner product of the vectors in the orthogonal basis only, right? And whatever you get out as for all the zero elements there is nothing to talk about, but for the non-zero elements you just get out norms, and they will eventually cancel out to give you one. This part is pretty obvious to observe. There's no explanation needed for this. Okay. Now, so we have given actually we already had precise knowledge about what a basis of a vector space is, and till this point we had no requirement of restricting a basis to certain conditions, uh, at least for orthogonality sort of concepts. Like previously we had constructed many different sorts of bases, for example cyclic basis, and then we had the Jordan basis and so on and so forth. All of them had some specific requirements, some specific importance. And this we have also formed one more sort of a basis which we are calling the orthogonal basis. So the obvious intuition is that it carries some special properties. And what is the typical special property? That is, recall we had a matrix representation of an inner product. So let V be an inner product space, and let alpha 1 to alpha n be a basis of it. Okay, so we are assuming a finite dimensional inner product space, be a basis of it. Recall that we used to give the matrix of the inner product as GKJ is equals to inner product of alpha j alpha k, right? Clear? So now if this basis is orthogonal, then what is the precise value of GKJ? Is delta jk, right? So this will come out to be delta jk or delta kj, whatever. But that mean that the matrix G, which is formed out of these elements G, K, J, is nothing but the identity matrix, right? Because delta jk will be equal to 1 if J is equals to K. Suppose this is an orthonormal basis. I mean to say it's an orthonormal basis, not orthogonal, an orthonormal basis. Okay. So if it's an orthonormal basis, then this matrix of the linear transformation, I'm sorry, matrix of the inner product is just the identity matrix. But if it's just the identity matrix, then recall from how we stated the uh, the expanded form of the inner product in terms of this matrix of the matrix of the inner product. If you recall, then we had sort of the inner product of a vector alpha beta, where alpha was given as summation xk alpha k, and this beta was given as summation yj alpha j. So this was coming out to be as uh, so it was coming out to y star gx as far as I remember, right? Where y star was the conjugate, right? Y star was the conjugate of the coordinate matrix Y, which comprises of these matrices, right? And X was the simple coordinate matrix of the uh, vector alpha, right? But then if G is identity, so if G is identity, then this is nothing but Y star X, right? It's just nothing but Y star X. But what is Y star X precisely? How can we write Y star X? So if you observe that this is nothing but summation over J, we had taken here right? Yeah, okay. Yeah, summation over k, you can write this as xk yk bar, correct? Yeah. But observe that this is nothing but a resemblance of the standard inner product of Fn, right? Correct. So therefore, if I consider an orthonormal basis of a finite dimension inner product space, then the inner product defined on that inner product space resembles the standard inner product of the n-dimensional field, right? And this field is nothing but the underlying field of this vector space we are talking about, right? Is it clear? Okay. Um, what more can we talk about in this lecture? Yeah, one thing I would be like to talking about, or rather I would want to introduce at least in this lecture, is the concept of a best approximation of some vector. Okay. So, uh, yeah, let's do that. So, using this concept of orthogonalization, we would want to define what we call the best approximation of a certain vector in a inner product space. Okay. Okay. So let's precisely give its definition. Okay. So a best approximation, a best approximation of a vector beta in V by vectors in a subspace W. Okay, is a subspace W. V is obviously an inner product space. So the best approximation of a vector beta in V by vectors in a subspace W. So it is a vector alpha which also belongs to W such that the norm of beta minus alpha is less than the norm of less than or equal to beta minus gamma for all gamma in W. So the literal concept of a best approximation by a vector beta by a subspace W is that vector alpha such that the distance between beta and alpha can be made smaller than the distance of beta with every element of W, every other element of W. Got it? Okay. Or the other way of saying this is that this so the best approximation of a vector beta is basically that vector alpha from W such that the distance between beta and alpha can be made as small as possible subject to the restriction that we are calculating the distances with respect to W vectors in W, and this alpha is an element from W. Okay. So this is precisely the concept of a best approximation of a vector, and there's a result regarding this best approximation, and that's the least thing which we can do to treat this in our course. Typically, the concept of best approximation is a very complicated situation that does not go with the uh, structure of the course which we are following. But the least we can do is this following categorization of what this best approximation is. We're not going to prove this in this lecture. We're going to prove this in the next lecture. So let me just precisely give the theorem of it. The theorem is as follows. Let W be a subspace of an inner product space V, and let beta be a vector in V. Okay. What I try to say is that a vector alpha in W is the best approximation to beta in W, or I mean to beta in W means to beta by vectors in W. That's precisely what I mean. If and only if beta minus alpha is orthogonal to W. That is, beta minus alpha is orthogonal to every vector in W. Number two, if if a best approximation exists to beta, then it's unique. Okay, best approximation exists to beta in W, I should say, in W. And number three is what is the most important part of this theorem is that if W is a finite dimensional uh, subspace of V and alpha 1 till alpha n. So we are talking about finite dimensional subspace, hence we can talk about an orthonormal basis. And if alpha 1 to alpha n is any orthonormal basis, of W, then the vector alpha is equals to summation over k. K obviously ranges from 1 to n. Inner product of beta with alpha k upon norm of alpha k squared times alpha k is the best approximation. Now we are saying is the best approximation because we already know that if a best approximation exists, it must be unique. So is the best approximation to beta in W. Okay. So let this lecture be up to this much. In the next lecture, we will be completing this part where we discuss the best approximations concepts, and in the next to next lecture we will be starting with the concepts of I have a multiple concepts in mind on which I want to make lectures on. For example, one thing which I have not covered in any of the previous videos is a complete detailed concepts on the system of linear equations. Right? What I actually want to do is I have two things in mind. I want to talk about the system of linear equations in great details in one or two lectures, or I want to talk about what we call the operators, the important operators, which are the concepts of unitary operators, we have the concepts of normal operators, and so on and so forth. Obviously, that's a part of inner product spaces, concepts related to inner product spaces only. So I am not sure yet what I'll do in the next lecture, immediately next lecture, but we'll have something interesting coming. So meet you guys in the next lecture.